Post-impact cue ball trajectory in billiards by Amadou Gueye, advised by Dr. Kolan. What is the trajectory of the cue ball after it hits an object ball? This seems like a simple problem at first, and we may be tempted to say a straight path at a 90-degree angle, but there is some difficulty. However, fundamental physics principles allow us to analyze similarly complex situations. In 1835, a mathematician by the name of Gaspard-Gustave de Coriolis wrote a comprehensive collection of principles about the physics of pool. One of these principles states the following. The curved path followed by a cue ball after it hits an object ball is always parabolic. Coriolis also remarked that in the absence of spin, the cue ball follows a perfectly straight path after impact. Before we try to illustrate this principle, let's first go through some definitions. The cut angle is the angle between the aiming line, the direction of the velocity of the cue ball before impact, and the impact line, which is the line that joins the centers of the two balls at the moment of impact. When the cue ball hits the object ball, the path it takes after impact is a straight line that makes a 90-degree angle with the impact line. This is called the 90 degrees rule and only applies when the cue ball has no spin. In our case, the cue ball will follow a curved path that is tangent to that 90-degree line, and we will see why shortly. Lastly, the final angle is the angle between the initial aiming line and the tangent line to the final cue ball trajectory. Let's now try to illustrate Coriolis' principle with VPython, where we simulate the cue ball impacting an object ball at a given speed and cut angle. As you can see, after impacting the object ball, the cue ball trajectory is curved. But how do we actually prove this? We will first derive the equations of motion involving linear and angular momentum after the cue ball impacts the object ball. Then using that, we will show that the trajectory after impact is parabolic. This is the translational equation of motion after impact, where F is the friction force acted by the surface of the table on the cue ball, and V is the velocity of the center of mass of the cue ball. The friction force is given by the following, where Vc hat is the unit vector in the direction of the velocity of the contact point between the table and the cue ball. We can now plug in the expression of the force. The mass terms on both sides cancel out. We are left with an expression that is the linear acceleration of the cue ball after impact. Let's now look at the angular momentum. This is the rotational equation of motion, where tau represents the frictional torque about the center of mass, I the moment of inertia of the cue ball, that of a sphere, and alpha the angular acceleration. The torque can be expressed by the following. This assumes that the cue ball is hit at a distance r from the contact point between the cue ball and the table that is straight at its center. We plug in the expression of the torque and notice that for the top view, the direction is to the left of the cue ball. Once again, we're able to solve the equation of motion, this time for the angular acceleration of the cue ball after impact. The velocity of the contact point between the cue ball and the table consists of the velocity of the center of mass of the cue ball, along with the velocity of the bottom point of the cue ball relative to the center of mass. When we plug it in, we get this expression. We now integrate the expression for the acceleration to get the speed as a function of time. This gives us the velocity vector of the contact point between the table and the cue ball during the curved trajectory. Taking vector components and integrating in time again, we find the x and y positions of the cue ball after impact. These expressions clearly indicate that the position of the cue ball at a given time t after impact will vary according to a parabolic path, as predicted by Coriolis. Let's now look at a cue ball striker object ball in real life and see if our model is right. Looking at it closely, we see the cue ball slightly curve immediately after impact. The final direction does not make a 90-degree angle with the impact line, further suggesting curving of the final path. Now, what really causes the ball to curve after impact? You can see from this side view that the cue ball initially has overspin and that the velocity of the contact point is in the direction opposite to the velocity of the center of mass. If we do not account for spin, We know by the 90-degree rule that the cue ball will have deviated in a straight line, but it is precisely because of the cue ball spins that it follows a curved path. At the time of impact, the cue ball has overspin in the upward direction. It retains that spin after collision, and it has also some component of spin in the right direction. Before impact, the cue ball has mostly linear momentum, and after impact, it has mostly angular momentum, meaning that the final direction is really dependent on the frictional torque about the center of mass of the cue ball due to spin. Another thing is that after impact, the cue ball has much more momentum in the initial aiming direction, which is the upward Y direction, than in the X direction. Therefore, the cue ball is going to be much more affected by friction in the X direction, which is why the cue ball is deflected in that direction. Now that we know why the cue ball curves after impact, here are a few things to note about our analysis. The spin of the cue ball about the z-axis would not affect the velocity of the contact point, and so will have no effect on the analysis of the cue ball trajectory. Furthermore, we do not account for the friction between the two balls at the time of impact, and we assume a perfectly elastic collision. Lastly, the cue ball is curved only when there is a frictional torque acting about the center of mass. Thank you for watching. I truly hope you enjoyed the video.